fused heterocyclic compounds. This is now you got heterocyclic compounds. They're fused together with other things on them, other functional groups. This is just to kind of show you where aromatic heterocyclic compounds are found in nature. They are very, very common. A lot of them are found in our natural environment, like we have L-tryptophan, which is an amino acid. All right, this is also the one that supposedly makes you like tired. You know, it's in Turkey. And they say I ate too much tryptophan. There is a lot of argument about that. Does tryptophan really make you tired, or is it because you just ate about 12,000 calories during Thanksgiving and you're basically in a coma, a sugar coma? That's what a lot of people think, because a lot of people eat like turkey like throughout the year. A turkey sandwich is so common, and you know, when I eat a turkey sandwich, I don't fall asleep. Okay, it's usually after the turkey dinner, a fireplace is going on, and I've been sitting all day long watching football, also drinking a little bit. I think that might have something to do with the fact that I'm tired, not necessarily the turkey. Obviously, that's kind of true, but you know, again, there's a lot of research. A lot of people argue, well, it's really not the tryptophan. But anyways, that's not the point. The point is that we have this aromatic compound right here that we've talked about, the 6,5, where the lone pairs are preoccupied. Okay, so there's the amino acid. We might get a chance to talk about the biochemistry part in this semester. If we do, if we don't, or if we do, an amino acid is exactly what it is. It's an amine group and a carboxylic acid group. So what makes an amino acid is, here's your amine group attached to a carbon. It's also attached to a carboxylic acid. And it's these groups right here that keep changing. Okay, there are 20 essential amino acids. There's ones that have a methyl group, they have sulfur groups, they have other things hanging off it. You have 20 of them. Okay, and that's what, but they all have a common structure where you have an amine group and a carboxylic acid. Okay, there's other compounds here. Here is LSD. Okay, if you notice that this kind of group is a very common group found in nature. Okay, notice in LSD, it's right here too. All right, there's actually been research done or studies done that actually kind of show that large amounts of tryptophan can have an effect similar to LSD. Okay, you can kind of hallucinate on these types of compounds, and it's kind of research where if you take something known, you know, because this kind of acts like tryptophan inside the brain. Okay, if you look, you have this part of it, all right, followed by a CH2, okay, and then another carbon attached to a nitrogen. CH2, a carbon attached to a nitrogen. So if you look, this part of it is exactly like this part right here. Let me actually get a pen here to just kind of show you. Okay, so this part of tryptophan looks very similar, or not very similar, is exactly like this part of LSD. Okay, now this doesn't have anything to do with the chapter, but I kind of want to show you how research is started, how a project would start. You kind of look at this and say, well, you know what if I started synthesizing things off of here? How about if I start putting more carbon groups off of here, or maybe attach something here? Can I synthesize something that's very similar to the structure of LSD and has like the same effect to it? The answer is yes. There are people who have done that have taken tryptophan and have changed the structure of tryptophan to see if it has a mimic. It's called a mimic to LSD. Okay, quinine, which is a anti-malaria drug. It's also found in tonic water. So there's a lot of people that don't like to drink tonic water because it has like a bitter taste to it. That's because of quinine. Okay, this compound is in your tonic water. It actually has like a bluish glow to it. If you've ever taken tonic water and you expose it under a black light, it will kind of have this bluish hue to it. It'll kind of look blue, and that's because aromatic compounds actually the photons are excited in aromatic compounds because it travels through like the p orbital, so it kind of has this bluish hue. So if you take tonic water and a black light and shine it, you'll kind of see that blue look. It's because of the quinine in it. But if you look, you can almost kind of see this type of group again, but a 6-membered ring in this case. All right, there's your 2 carbons with a nitrogen. There's an OH in this case, but see, it's very similar to these types of drugs. Okay, So pretty interesting. And then on this one, you can see also there's aromatic. So this chapter is about aromatic compounds, but I'm kind of giving you a medicinal type of lesson as well. All right, common names. These are common names. We do get a little bit more into naming next chapter, I believe, but these are just common names of how you name aromatic compounds. Okay, so you have your benzene ring, which is kind of, you know, what this chapter is all about. Okay, now if you have an OH on your aromatic ring, it has a special name. It's called phenol. Okay, that's a common name. So rather than calling it hydroxy like benzene, okay, or that name I've never seen before, but it's just called phenol. All right, methyl benzene is called toluene. All right, that's the shorthand for that compound, toluene. It's a common name. This is called aniline. This is anisole. All right. Anise, you've probably heard the term anise. Is kind of, if anything has anise in it, it has like a black licorice type of taste to it. All right, because this is the main structure of that taste of black licorice. All right, is this compound? It's pronounced anisole, so it's actually not anise. It's anise. I mean, there are people that pronounce it anise opposed to anise. So however you want to pronounce it, it's the same thing. Styrene. This is styrene, aromatic ring with a double bond. You have heard of polystyrene. Polystyrene is like foam or styrofoam. Well, styrofoam, the styra part comes from styrene. So that's an aromatic ring with a double bond. Acetophenone is methylphenyl ketone. That's just a common name. That's benzaldehyde. This is actually a main ingredient in almonds. Not the main ingredient, but it's what it gives almond its smell. If we have time in lecture, remind me, and I'll get the bottle of the a benzaldehyde, and you can kind of smell it. It has an almond smell to it. And then benzoic acid. Okay, what I want you to do is I want you to memorize a few of these. You don't really have to know anisole because it's not that common. So actually, I'm going to put an X through it. And styrene and acetophenone are not things that you have to memorize or have to know. You will see them. But phenol, toluene, aniline, benzaldehyde, benzoic acid, these are much more common. I want you to memorize and know those. Okay? And you'll kind of see why. All right, disubstituted benzenes. What happens if you have a disubstituted benzene? How do you name it? Well, there's kind of an old-fashioned name. It's a common way of doing it, and most people name it this way. If you have a 1,2 substitution on your aromatic ring, that is the ortho position. People call it the ortho position. They're ortho to each other. Rather than saying 1,2 dichlorobenzene, you just say ortho dichlorobenzene. All right, you sometimes write it with an O instead of write the word ortho. You can write the word ortho, or you can just say O. All right, if you have 1,3, it's called meta. These are meta to each other. Okay, so in this case, notice this is my common compound right here from the last slide. That it has a common name to it. That is benzoic acid. Okay, but it has a chlorine on it. So the parent name to this is benzoic acid, but at the meta position, or at the 3 position with respect to this is always assuming this is 1, 2, 3. You would say metachloro. Oh, it's actually a peroxy. Sorry, I didn't notice that 3 there. This is a peroxy benzoic acid. All right, but sorry about that. So peroxy benzoic acid. You don't have to know that, but the benzoic acid part you do have to know. You have a chlorine at the meta spot. So let me actually just go here. So if you had this compound, let's just put a bromine, and let's just put a regular benzoic acid. That would be called meta-bromo benzoic acid. Okay, or you can just call it 3-chloro-benzoic acid. It doesn't really matter, but like I said, most people use the meta and the ortho. This is a phenol right there, including the OH. That's a phenol group. Opposite at the 1,4, it's called para. That's the para position. So you call it para-nitrophenol or just 4-nitrophenol. All right? So ortho-meta-para. What happens if you have 3 or more substituents? Use the smallest numbering possible. Okay? But the most oxidized carbon with a functional group is your number 1. Okay? So how does that work? My lowest numbering, in this case would be here 1, 2, 3. Okay? And the number 1 carbon in this case is the phenol. What this means, the most oxidized, means the carbon that's attached to the most oxygens. Okay? Or the group. It's actually better the group that has the has the most oxygen. So in this case, this happens to be our parent compound. Okay, that's our parent, so it's a phenol. Okay, and the lowest numbering would be 1, 2, 3. So it's 2,4-dinitrophenol. This one's kind of obvious. 1,3,5-trinitrobenzene. Okay, this one you have a benzoic acid. What this kind of means is like which one is our parent in this case? Is it my phenols or my carboxylic acid? Well, the group that's most oxidized is your parent. So since the carboxylic acid has the most oxygens, that's the most oxidized, that's my parent. All right, so it's 3,5-dihydroxy, because these are hydroxyl groups, benzoic acid. Okay, let's name this compound. I want you to name this compound. This is kind of practice. It's based off of this. So we'll put a CH3 here, and then let's put 3 NO2 groups right here. All right, so put this on pause and see if you can name that compound. Welcome back. If you have not paused, then put it on pause and then come back once you name it. Okay, this is going to be called, so was is called. All right, what this is this is my parent compound right here. It's toluene. This is a toluene group. So that's where my that's where carbon 1 is starting right there. Okay, so I'm starting, because in this case, this is my parent compound. You always start numbering at the parent. Okay, and then you have a 2, 4, 6. Okay, so this is 2, 4, 6. We're going to write it. Let's write it up here. 2, 4, 6. Trinitrotoluene. Okay. This is also known as, there you go, TNT. Okay. So you might be a little confused because this is a little weird. This kind of statement is really only used, so if you have a parent, if you don't have a parent, like for example, let's say this nitro group is right here. Okay. The question is, where do you start counting? You start counting, that gives you the lowest number. Okay. This is now saying that you start with the functional group as your number 1. Okay. So there is no name for an aromatic ring in a nitro group. So you have to, so this is my parent. Whatever your parent is, that group is your number 1 carbon. Okay. If you did not have something for a methyl, like let's say I had an ethyl group here, then I would start numbering at this carbon, because that would give me the lowest numbering, or start at this carbon. It's the same thing. Okay, so that's what that means. If it's still confused, we'll talk about it in class. Here are common names for disubstituted benzenes. There's something called xylenes. There's orthoxylenes, metaxylene, paraxylene. You have 2 methyl groups. All right, this one we're really not going to worry about. I don't really want to worry too much about these. Just know that they do exist. But I don't want you to know these or to memorize them. Okay. A phenyl group or a benzyl group. I'm going to put this on pause and start a new video because we're running out of time. Because I want to spend a little bit more time on this slide. So I will see you at the next video.